Okay, so let's take a look at a few example problems that involve secants and tangents and the angles formed by those things, segments involved with those things, all that stuff we learned in section 10.5. Let's look at a few example problems that goes along with that. All right, in example 1 here it says to find the measure of angle BEC. So we can look at that angle and we can realize that that's an angle it's formed basically by two secants. Now, in the picture, it's actually formed by two chords, but we talked about how if I take a chord and I extend it in both directions, then it essentially makes a secant, right? And so I do have an angle here that's being formed by two secants, so I know that the measure of angle BEC will be half of the sum of the angle that's intercepted, of the arc that's intercepted by that angle, which we can see that angle there is intercepting arc BC. So it's going to be half of that arc's measure and the arc measure of the arc that's intercepted by that angle's vertical angle. So its vertical angle would be angle AED right here. And we can see that that angle is intercepting arc AD, which is 60. So to find the measure of angle BEC, we just do half of 86 plus 60, which would be half of 146, and half of 146 is 73 degrees. Now, in example 2, it says that we need to find the measure of angle PQR. That's right here. And it does say that my two rays that are making that angle are tangents to the circle. So this is another situation where we have an angle. Well, actually, in this situation, it's different than this one. In example 1, our vertex was inside the circle. So we used this idea of adding two arcs and dividing by 2. Now we have an angle whose vertex is outside the circle. So we know that the measure of that angle is going to be half of the difference between two arcs, the two arcs that are intercepted in that circle by that angle. So with a tangent, our two arcs that are going to be intercepted are this big major arc right here, which it doesn't say that we have a measure for, and this minor arc right here, which it says is 125. But if we look at those two arcs, right, this minor arc here, and then this major arc right here, what you'll notice is that if you put those together, they do make the entire circle. So this arc measure here would be 360 minus this one, so minus 125. So that's going to be an arc measure there of 235 degrees. So that's the number that we're going to put in right there. So this angle is going to be half of the difference between this 235 degree arc and this 125 degree arc. So that's half of 110 degrees, which is going to be 55 degrees. Now in this next example here, in example 3, we have to find the length of a segment, right? We need to find this segment right here, put an X there, and we notice that we have a point outside my circle, and then we have a segment drawn from that point to this point on the circle, and that segment is 8 units long. Then we could look at the segment that's going from point H to point F, which is kind of like in the same direction as segment HG, but it's going to the opposite side of the circle. And then we have a tangent segment, or a tangent over here. Now, in this scenario, we learned that if I take the length of segment HG and I multiply it by this length of this longer segment that's going to the opposite side of the circle from where G is, so that would be segment HF, that should equal the length of the tangent segment squared. So now if I substitute in numbers for these measurements, we could say 8 times HF is x plus 8, because this part is, I said x. So HF is x plus 8. And then that's going to equal this side, which is 12 squared. So I got to take 8 times this quantity, which means I need to use the distributive property. So I'm going to have 8x plus 64, and that's going to equal 144. And then if I subtract 64 from both sides, then it'll say 8x equals 80. And that leaves x to equal 10, and x was the value that I was trying to find, the length of GF. So that side is 10 units long. Now in this problem here, we have another point outside the circle, and this time we have like two secant segments. We have a secant segment that's hitting the circle at L and then again at M, and we have a secant segment that's hitting the circle at P and then again at N. So in this scenario, if I take the length of KL and I multiply it times this longer portion of that secant segment, which is KM, then that should be equal to this segment KP multiplied by this entire segment KN. And we have to find LM, so I'm going to put an X there. And let's substitute values for these lengths. KL is 6. KM is X plus 6, right? This part plus this part. KP, it says, is 7. And then KN would be 16 units long because it's 7 plus the 9. And then if I use the distributive property, this side turns into 6x plus 36. And then 7 times 16 would be 112, I believe, because 7 times 10 is 70, and 7 times 6 is 42, and 70 plus 42, yeah, that's 112. Then I can subtract 36 from both sides. 112 minus 36 is going to be 6x equals 76. Then I can divide the 76 by 6, and x equals, basically it's going to be 12 2/3. If you do it on your calculator, you get 12.6 repeating, which we can say is 12 2/3. And then finally we have example 5 here, where it says that segment AE is a tangent, so this is a point of tangency, and we have to find BC and EF. Well, if that's a tangent, then basically what we have is kind of two scenarios where I'm looking at first point A, and I'm looking at this secant segment from A to C, and this tangent segment from A to F, and I'm going to think about the relationships between the parts of that diagram. I'm going to kind of ignore all the stuff over here for a second. And that would tell me that if I take AB times AC, the secant segment in its entirety, then that should equal AF squared. Because again, I'm pretending that all this stuff doesn't exist. I'm just looking at from A, I got this secant segment and this tangent segment to F. I'm going to put an X for BC. I'll put a Y for EF later. AB is 2. AC is X plus 2. AF is 4. I squared the 4. I'm going to distribute the 2, so that'll be 2x plus 4 equals 16. Subtract the 4. 2x equals 12. And x would equal 6. So BC has a length of 6. But now if I come over here and look at this scenario, I have a secant segment, I have a tangent segment. So I know that if I take this part of the secant segment, the external part, ED, times the entire secant segment, EC, that should equal this tangent segment squared. So ED has a length of 4. EC has a length of 9, and then EF is y, so that'll be y squared. 4 times 9 is 36, so 36 is y squared. So y would be the square root of 36, which is 6. So segment EF has a length of 6.